Welcome in. All right, so let's do a little bit of thinking here. We want to be able to try to derive the derivative of ln x. And so ln x is nothing else but simply a logarithmic function, okay, that we have. And you can think of it as simply log of base e, and we have our input as x, and we will write this as ln of x, where that particular e, so Euler's number, is just assumed to be the base. Now, what you see on the screen is actually the function graphed. So if you would have graphed this particular function, f at x is equal to ln x, this is exactly what you would see, and typically those brackets are dropped, and we know that it's an argument there. Now, you can also write this as simply y is equal to ln x, which is very convenient, sometimes just simply as a relation instead of an actual function. And you know, or at least you should kind of know if you have studied logs, okay, so throughout, you can certainly deduce that our domain, so for this particular function, is x greater than 0. So it can be anything that's positive, but it can't be negative and it can't be 0. And that is just simply because of the fact that we're talking about kind of the inverse of the exponentials. Now, in this video, I don't want to go too far into trying to talk about the function itself, but I do want to talk about derivatives. So if you're in grade 12, and I hope that your teachers show you this, but if they don't, okay, you're going to see it in this video. I love to try to derive as many of the derivatives as I possibly can, just to show students, you know, how can you come up with the actual proof of the derivative. And for this one, it's not that bad so long as you're comfortable with implicit differentiation. Now, there's other ways you can do it, but implicit differentiation is definitely one that I like to utilize. It's one of the simpler ones that I understand. And I can put up a link up above there for you if you want to go over implicit differentiation again for yourself, because that's something that I'm going to be using in this video. So in short, if you would have studied, okay, this particular relation or this function, ln, okay, of x, and you wanted to take the derivative of this, you will find out that the derivative of this, so if you take d, okay, of ln x dx, in this way, you will find that it's rather strange. It is actually 1 over x. This is what it would be. Now, remember what the derivative means. The derivative means that it's the slope, right, at every single point. So if you looked at this function, maybe it wouldn't be so strange, especially for, you know, all the x which is greater than 0, that this would have been the derivative. So you notice, okay, that if you're very close to 0, that ln of x just starts to skyrocket downwards, right? It goes more and more negative. But if you're thinking about the slope at that, okay, so basically it gets more and more vertical, and then as it comes out, kind of peaks out in this way, and then it flattens out in terms of the slope. And 1 over x, I'm sure that you remember, I'm only going to talk about it and graph it for x is greater than 0, so I won't go on the negative side. But basically it looked something like this, right? So it looked something of this nature. Let's see if I can, it doesn't let me swing it out, but maybe I can. Let's see. Okay, so it's a little bit better. So it kind of looks like this, right? And of course this goes on to infinity, and this just simply approaches 0 as it gets closer and closer. And that's what the actual derivative is. It is nothing else but 1 over x. Okay, so now how do we come about with that? You can memorize it, right? Okay, so ln x, the derivative is 1 over x. Not a big deal. It's certainly better than trying to remember some of the trigonometric functions, right, that you have, especially beyond, like if you're talking about secants and cosecants and so on, which I often forget myself, and I have to rederive them. Now, anyways, so for this one, if you're going to take this, I'm going to use implicit differentiation in here. So I'm going to copy this, I'm going to bring it back down here, and my goal is to try to derive how this 1 over x comes about. So what I'm going to do is I'm going to do a little bit of a trick in here, and because I know that ln k of x If I raise it to, okay, so if I raise both sides of the equation, okay, and I take e to the, okay, so this is going to be e to the ln x over here, and then e to the y. So I'm not really doing anything except just putting the actual left-hand side as my exponent, okay, so in here, so notice the y appears right there, and then the ln x appears right there, and clearly the left-hand side and right-hand side are still equal, so I haven't done anything. But this is a trick maybe that you haven't seen before within here. So that's the first thing that I'll do. Now, if I do that, then this is going to drop off on us because e to the ln x, right? So this is nothing else but e log ex. And we know that this is just simply equal to x from our properties. So those are our log properties. I can put up a link up above there for you to the log properties in general, but this is just a simple log property. So this really is just e to the y, and then I have my x which falls off. And now if I take the derivative, now I'm going to take the derivative of both sides, okay, of this. And so on the left-hand side and the right-hand side with respect to x, okay, so I'm going to take that. And that is going to be using implicit differentiation in here. Okay, that's where I actually need it. So if I take the implicit differentiation, then what I'm going to have is I need to know what is the derivative of e to the y. Well, the derivative there is just e to the y because that's what the derivative of e is. But it's also going to be multiplying by the dy dx, okay, so this is the implicit differentiation that we have. On the right hand side, well, the derivative of x is just 1, okay, so this is just going to be 1. And now what you may notice that, hey, wait a minute, I mean e to the y, so this right here, so what that is, okay, so e to the y, and you'll see that from right here, that is just simply equal to x, okay, so that's from that. So I can substitute, okay, and just say, okay, so this is x multiplied by dy dx is equal to 1. And now, of course, if you isolate for the derivative, so this is going to be dy over dx, or simply just y prime, and this is going to be 1 all over x. And this is exactly what the derivative would be, right? So that's actually how you would find the actual derivative, and the proof is just by implicit differentiation. So those are the actual steps that you would have here. Now, I actually plotted this just before, so I want to be able to show you also on decimals, okay, so this function. So let me plug it out here. So here is my ln x on the left hand side, so you see that. And then I just, basically on the left hand side, I just defined a point. So I'm trying to find all the points here. So here's the point, and I can move this point around here, right? Now, of course, it's going to just drop off there as it gets closer. And now, notice that the slope that I put, which I defined as m, so that's on the left-hand side, so m is equal to 1 over x, correct? Okay, so that is the actual derivative of ln x. So I want to know what the slope is at every single point. Well, that's going to be 1 over x. Now it's 1 over a because a is my x value, okay, that I have in there. And then what else I'm doing there is I'm actually finding b. So I'm finding the equation of the line at the point. And b, which is the intercept, so the y-intercept of my line, is going to be nothing else but y minus m times x, okay, and then you substitute the point itself. And so here, so if I have it in there, so notice now on decimals I can actually make this, okay, and you will see that, hey, wait a minute, this is pretty cool. So here is the actual derivative at every single point. Now, of course, as I get closer to 0, and I probably have to zoom in here, okay, just so that you can see how it nicely captures that slope. And there you have it. So you can utilize, okay, this, okay, to basically find out what the actual derivative of ln x is. And now you know where it's coming from if you're comfortable with implicit differentiation. The proof is actually relatively simple in comparison to many of the others. All right, thanks for watching, and we will see you in a future video. Happy studying for calculus. Bye, everybody.